G'day, in this video we're going to be unpacking some experimental evidence for time dilation and length contraction. This is our final video on dot point 7.4.2, certainly the most consequential one for inquiry question 4, which asks about the behaviour of light and how it affects the concepts of time, space and matter. Again, we're finishing off time and space. We've been learning about length contraction and time dilation, and our key aim today is to look at some situations where it's actually observable. Our two key focus areas are going to be on cosmic origin muons and the Haffel-Keating experiment. There are also two other examples that are in our syllabus. We could also look at particle accelerators and cosmological studies, and we might dabble on those a little bit more in class. However, the first two are much more significant and will be our primary focus area. So we'll be looking at that real-world evidence which supports time dilation and length contraction. Let's get into it. So the first experiment that we're going to look at has to do with this particle called the muon. Now, a muon is a subatomic particle, but it's one that you're not likely to have heard of before, and is a particle that we'll be learning about towards the very end of this course. Now, you don't need to know everything about the muon today, but what's really important is it's a subatomic particle and it has an extremely small half-life. They don't exist for very long at all. It has a half-life of 1.5 microseconds. What that means is if I have a collection of muons, let's say I have 100, every 1.5 microseconds, half of those muons will essentially decay and no longer be muons. So in 1.5 microseconds, there'll be 50 particles left. In another 1.5 seconds, there'll be 25 particles left. In another 1.5 seconds, there'll be 12 or 13 particles left, and so on. What this means is that on average, a muon exists for 2.2 microseconds and then it's gone. So this might raise a couple of questions. Why are we doing experiments with a muon if they don't last for very long? And where do they come from? So for their origins, we'll be looking up towards the sky. We're talking 10 to 15 kilometers above sea level in our upper atmosphere. Solar radiation can enter our upper atmosphere and strike particles which are there. Now, when that radiation interacts with those particles, it can break the particle down into chunks, releasing out a spray of muons, some of which end up traveling towards the surface of the Earth. Muons traveling at the speed of light will only travel about 660 meters if they exist for their expected lifetime. Now, obviously, this is quite shy of the 15 kilometers that these muons need to travel. Yet, interestingly, we are able to find and detect muons which have come from the upper atmosphere on the surface of the Earth. So the question becomes, how does this happen? These muons are existing somewhere between 25 and 30 times more than their expected lifetime, statistically meaning that we really shouldn't detect them on Earth, yet we do. So in comes the Freisch-Smith experiment. Essentially, these two scientists took a muon count on the top of Mount Washington, which is in New Hampshire, and the peak is about 1,917 meters above sea level. We can see it in the picture over here. We can see it in the picture over here. And at the peak, they found that they could detect within the space of an hour, on average, 563 muons. And that these muons are traveling at the speed of 0.995 the speed of light, which again, based on our estimate, means they should really only be traveling about 600 to 650 meters. So how they were traveling for kilometers and kilometers is a little bit odd. Based on the math for the half-life of the muon, they predicted that they should be able to detect 27 muons per hour if they repeated the experiment at sea level. What they found, however, was that when they went to Cambridge in Massachusetts, which is in Boston, quite close to Mount Washington, and repeated the experiment, they didn't detect 27 muons per hour. They instead detected 412 muons per hour. So the question becomes, why did so few of these muons decay? Well, the muons were traveling at near light speed. What that meant was that special relativity had to be applied. What that means is the time experienced by the muons going from the top of the mountain to sea level was much less than the time they assumed the muons would be traveling based on their speed and based on Newtonian physics. Therefore, over that shortened time period, less muons decayed than expected. Another way of explaining this as well is through length contraction, and that's the idea that the muons were able to move through a contracted space, so not 2 kilometers, but a shorter space than that, and travel through that distance. Therefore, it meant that the muons arrived in less time than was expected. And again, there were fewer muons decaying. Whichever way you look at it, you get to the same conclusion. And so when we account for this shortened time period and contracted space through which the muons are able to travel, we are able to quantitatively account for why we get a lesser rate of decay compared to the expected result. And thus, Einstein's theory of special relativity no longer exists in the theoretical, but is rather observable through measured results that we can see here on Earth. Another experiment that demonstrates the concept of time dilation is the Heffel-Keating experiment. Here they are with their atomic clocks in tow on a plane. Now, we might get into how atomic clocks work a little bit more in class, but suffice to say they are exceptionally accurate. In this experiment, we're going to be measuring time differences to the nanosecond, which these atomic clocks will be able to account for to very, very high precision. In this experiment, 3 sets of atomic clocks are placed in 3 different locations. 1 set of clocks are placed on Earth and remain on Earth for the entirety of the experiment. Another set of clocks is placed on a plane that flies around the world in the same direction as the rotation of the Earth, in an easterly direction. And the third set of clocks flies in the opposite direction against the rotation of the Earth to the west. In this experiment, it's really important to understand that all clocks are considered to have a velocity in the experiment, including the clock on Earth, and that's due to the Earth's rotation. Therefore, the difference in velocities of the clocks on the planes depend on whether they're traveling with or against the rotation of the Earth. In other words, the velocity of the clocks on the eastward plane have a velocity of the rotation of the Earth plus the velocity of the plane. The velocity of the clocks on Earth have a velocity equivalent to the rotation of the Earth, and the clocks traveling west have a velocity which is the rotation of the Earth minus the speed of the plane. For our clocks traveling east at the greatest velocity, they experience the least amount of time, and therefore the atomic clocks read a time less than the reference clocks, which are stationary on the Earth. For the clocks that are traveling west, out of all of the sets of clocks, they travel at the lowest velocity, therefore they experience the largest amount of time, the most dilated time. And as a result, when they land and their times on the atomic clocks are compared to the others, they have the largest times for a reading. And this is, roughly speaking, what we can see in this table over here. However, something that you'll notice is that the differences in time compared to the reference clock are quite different for the eastward and the westward journey. You'll also notice that this was a phenomenon which was already predicted. And this is because this experiment didn't just prove special relativity and time dilation specifically, but it also proved general relativity, which had already been developed by Einstein by this time as well. In the theory of general relativity, gravity also has an impact on time experienced within a frame of reference. What this predicts is that objects experiencing less gravity, like the planes which were at a higher altitude than the ground clocks, would tick faster than the ground clocks and therefore measure an inflated time compared to the ground clock. As a consequence, the westward plane experienced 2 relativistic effects. The special relativity effect increased the perceived time and dilated the time, as well as the general relativistic effect of gravity. Therefore, we got a big difference between the westward clock and the reference clock. For the eastward clock, there were 2 effects which were opposing each other. The general relativity and gravity effect increase the measured time, whereas the special relativity and time dilation effect decrease the measured time. As the eastward clock still measured a lower time than the reference clock, what that means is, in this experiment at least, the special relativity and the time dilation factor had a greater impact than the one for gravity. In a scenario where the eastward journey had a plane traveling faster than the reference clocks but did so at a significantly lower altitude, let's say we had a train that was able to travel around the equator, for example, we would find therefore that the difference between the eastward journey and the reference clock would be much greater. Thank you very much, everyone. In the next video, we're going to be looking at how special relativity has an impact on mass and momentum. But until then, have a good one.